meetings overrun.
Yeah.
Cool. Thanks, Florian. Okay, so I'll just do a quick run over the agenda. So yeah, Jorge is going to talk about Kelmarsh Wind Farm Unplugged.
Yeah.
So a risky journey into the nacelles and SCADA-based failure data with a quick stop in Monte Carlo. So that should be pretty interesting. And it's all based on the Kelmarsh dataset, which is one of the open datasets.
Exactly.
That we've also used in this group previously. Next week, I'll do a couple of announcements. Next week is a kickoff for the Hill of Towie open dataset. So if you want to join the Res group and Alex Clerk, then he's kicking off a challenge based on that new open dataset. So I'd recommend joining if you're interested.
Yeah, of course.
And then I've had a request for help on Enercon turbines. If anyone's got experience with connecting to Enercon turbines and collecting the data from them, there's a community wind turbine, which Andrew Garrett of Garrett Hassan history is running, and he's looking to get the data from that turbine and then potentially release it. So if anyone's got experience of pulling data automatically from Enercon turbines, that could be very useful. And then finally, there's going to be a I've forgotten what so there's the, maybe Florian can remind me what it's called, the science project, the Swiss Institute.
Oh, wait, yeah, I will check and hopefully find the link or something.
Yeah, cool. We can come back to that at the end of the call. But basically, there's a project run with a science centre, and they're going to allow us to experiment with some different platforms that we can use to run challenges in the future. So can come back to that at the end. So for now, I'll pass across to Jorge. If you'd like to do your presentation.
Well, thank you very much. Thank you very much. Yeah, I mean, let's jump to the presentation, because there I have a point where I discuss about me and I talk what I've done really quickly in 2 slides. So let me share here. Let me share a window. Okay. So let's do slideshow. Okay. So are you seeing that?
Yep. Yeah, that's good.
Okay, we're on the same page. So Kelmarsh Wind Farm unplugged, really unplugged. Okay, a risky journey into the NASA's and SCADA-based failure data with a quick stop in Monte Carlo. Oh, my name is Jorge Thomas. Okay, this is the content of our risky journey. Okay, and about me, I'm not a professional gambler by any means. My motivation, there is last year reading a final report of a project where I was shortly involved, okay, of planning a wind farm. I just read the results and I was questioning some things that we'll see. Okay, there is value here. Okay, and what about digital twins? Now there are something's missing. Okay, the scope: Kelmarsh Wind Farm, 12.3 megawatts. Host outages are stochastic. Common failure modes, just counting labeled events. Nothing is normal. Operational repair times, time state diagrams, time to failure, bathtub, yearly failure rates, time to repair, yearly repair rate. A quick stop in Monte Carlo, state duration sampling, system generation capacity curve. A blackout is bad luck. Big questions and vision. How do I combine these? And some takeaways: you can't always get what you want, but if you try sometimes, you might find you get what you need. Right? So, okay, about me, quickly. I'm not a professional gambler, or am I? I started very young, 23. I'm an electrical engineer from Venezuela. I started in the world of maintenance engineering, okay, as analyzing risk and reliability of complex meshed networks, okay, power generation and transmission systems, high voltage. And yeah, I mean, first task was to write a helicopter without doors to collect data of corona effects in transmission lines, 400 kilowatts and 800 kilowatts, which was more risky than studying risk. And then, that was in Venezuela for the operator and owner of at that time, the third largest, now today the fourth largest hydropower plant in the world, WeDoWind. And I did a lot of data analytics and commissioning of battery energy storage systems. Then I did my master in renewable energies technologies in the University of Nottingham in UK. So I specialized in photovoltaic, wind, everything sustainable, electrical engineering, power electronics, and forecasting of resources. And then I worked at KIT here, and I am now in Germany, in Karlsruhe. I was responsible for the photovoltaic field, 1 megawatt at KIT research, and developing algorithm in order to forecast solar irradiance and solar power generated, control battery energy storage systems. And then I worked 5 years at Fraunhofer. And now I hold strategic project-based role as head of risk and forecasting for power and energy systems within the Science and Technology Division of Alicios Corporation. However, I'm open to work in a normal daily basis too. Yes, that's a brief resume of around 20 years. I started really. So this was my first master thesis in Venezuela. The problem here you see is you see 2 transmission lines here that they are crossing a lake, okay, 400 kilowatts in parallel. And the problem is that these 2 transmission lines, you can see the size of this thing. This is a small cargo ship. They are really a lot of failures. Okay, they are out a lot of time because of storms, okay, flashes and storm-related outages. And the big problem here, how can I model this? Because when there is stormy weather, you can't your failure rates just go so high, so it's not like non-Markovian process because you don't have a constant failure rate. But there are ways to classify this in different stages, and you see here the chain how you have to divide what is normal weather here on the upper hand, on the upper side, and on the down side you see the adverse weather. Okay, and you modeled all the combination of the availability and unavailability of each transmission lines, and you can play with that. Okay, so you can treat it as a Markovian with a big matrix, stochastic transition matrix. This work started 20 years ago, exactly 20 years ago, 2005. And today I'm so happy to be back at it with new and more efficient methods, tools, experience, and questions. Okay. So what was the motivation? Why I picked up this data set? Okay. First of all, I was curious and I searched for a complex data set to learn data wrangling with polars. Okay, I don't like pandas, and so I look for it's a relative newer data frame library for Python. Okay. But reading the final results, this table that you see here, okay, these are the final results from a real project last year. Okay, a wind farm with 16 wind turbines. That's okay. This is the installed capacity of the wind farm. You see here the gross energy production, which is okay. Once you, this is calculated with the WinPro and such and those type of software, no, for planning. So this is due to the wind availability on site. Okay, then this is cool. I mean, this is with the wake losses, no? Again, with simulation. Electrical efficient 3%. I don't know where does it come from, but I suppose you can fair enough. You can calculate that depending on the size of the collector system, etc. And I started reading here availability. It should be on availability first, no, because 3%. It's a very round number. A very round number. How did they do that? I mean, are these standards? Are these where does it come from? Other factors 1%. Utility downtime 3%. Why? Okay, where does it come from? No, estimated annual net energy production. Okay, this is a consequence of this, let's say, degradation in the capacity factor. And you have a 42% capacity factor and the estimated 42% of a year in, I mean, of 8,760 hours per year. No. And so these are typical, I mean, this was the final report. These are typical planning values that you're going to find with done with different contractors and different companies. No? So value, okay? Let's think about this index, the estimated energy not supply, and how with the electricity costs, it transforms to EDC, estimated damage costs, okay? Which is much more informative. If you think about that, I mean, this is really there's a lack of information here, okay, for investors. No, I mean, we're talking about planning a big wind farm, okay, and now I thought about the second market. There is a lot of transaction with used and refurbished wind turbines. Yeah? And I thought, wow, when we buy a car, the first thing that we ask is, okay, but how many kilometers does it have? I mean, how old is it? The machine, kilometers? Okay, and how do you quantify that for a wind turbine? Okay, if you want to buy refurbished. So basically, I mean, this information is gold for investors. Okay, I mean, that's the first thing to know about the historical of each unit. Moreover, okay, I've programmed digital twins, and I realized that digital twins are not incorporating probabilistic parameters. I mean, when we see the open libraries in Python, okay, well, okay, or you developed an object that resembles a wind turbine, I've never seen properties related to probabilistic parameters. There's no space for that. Okay, it's like, okay, I don't know why. I mean, today with all the amount of data that we have, and all this was my motivation. Okay, to start digging a little bit about this. Okay, let's see the scope. Okay, well, we are in Kelmash wind farm, 12.3 megawatts. Construction completed in April 2016. Very important to know that. And we're talking about 6 2.05 megawatt Senvion MM92 turbines, which they made today serviced by Siemens Gamesa. Senvion is not there anymore. We're making turbines. The data is 385,000 SCADA event records sorted from Greenbyte. Today's is power factor because they bought it. Also known as Charlie's dataset 2016-2022. So we continue with this scope. Okay, here is how this standardized categorization of events. Okay, we have different events. We have requested shutdowns. We have something called known. Forced outage, we have full performance, out of environmental specification. For instance, where there's you are out of below cut-in wind speed. Partial performance, there is CO there. Technical standby. Okay, partial performance, okay, due to grid, because there are 37 curtailment here. Okay. Technical standby, 3,094. What's that? scheduled maintenance 818 events, okay, out of electrical specifications 371. I just took 892 events, forced outages, not with a stop. No, I don't care about warnings. Stop. Okay. Why? Because I know that these are truly probabilistic, stochastic. If we think about scheduled maintenance, okay, if we have the information about the stop and the plan, we can just add that time because we know already. So you can treat it. It depends. You have to analyze the data, but it depends on whether you are considering that to be stochastic or non-stochastic, depending on the plan and the scale. So this is the scope, 892 events. So common failure modes. This is a quick review only of those forced outage events. We have this frequency converter not ready. It's a really annoying failure because I realized that, okay, this is a 2 minutes, 2.5 minutes reset that somehow the converter, I don't know if it's part of the synchronization with the grid, if waiting for a signal to synchronize, I don't know, but it's really, I mean, it's very frequent, but very short. So it's not that important. More important, I consider, is this. I mean, maybe this frequency converter already. I mean, it has to do with the operating system of the machine, but it's a way. It's part of the routine to try to do something there. Okay, but it's cataloged as a forced outage, IEC. We have anemometer defect, which was very common in some turbines in Sandmion, and tower oscillation, manual stop, frequency converter error, pitch run away, safety chain open. You have a list of those failure modes. Yeah. Nothing is normal. When I mean nothing is normal, I mean Gaussian. Okay, in operation repair times. So forget about mean and median. They are very different in this type of the statistical nature of these events. So we have time state diagrams. Okay, we have here, for instance, it's amazing how even though they lie next to each other, we have, for instance, turbine one. Okay, this is operating time, and then you have a failure. No, they lie next to each other. How different are the natures of this type of events? This is operation time or time to failure, and this time to repair event. Time to failure is hardware, software dependent, turbine assembly and architecture, power electronics complexity, number of components, configuration, and time to repair is generally human dependent in general. Available spares and components, logistics, maintenance, service providers, team size, very different. I mean, they are next to each other, but they are very different. No? So I don't know if this works here. Yes, so I have a more interactive report because I have the diagram here. If you are seeing this one, you can see, for instance, 2019, and we can zoom here, and you can see this failure here, the event. Okay, turbine was working, and then you can see the repair time or the time that took to clear the failure. Okay, and you have different. Okay, look, this probably was the grid. Look, all the 6 turbines at the same time. That's really so it was a grid failure for sure. So you can see that there is a link here. I will show you later, so you can just play with this report in a more interactive way. So let's continue with this full size presentation. Okay, so very different nature in these two events for these 2 events. Let's talk about failure, okay, or let's talk about frequency of failure, about failure rate. Here is the theory, typical the bathtub curve. You know that when you start a system or you are commissioning a power plant, you have a lot of early infant mortality failures. Okay, and with the time you can play around with a constant failure rate, which is what I was looking for with this analysis. I was looking, okay, what's the constant failure rate? What's the constant, what's the baseline, okay, related to hardware related failure? What's my baseline with this type of turbine Senvion MM92? So basically, I calculated individually the yearly failure rate, and I know that, I mean, it was a rough start, okay, but then it stabilized. There's a more stable period here, and in 2022 there were, the turbine number one, it had a lot of problems with the anemometer, so it's an outlier, okay. So it doesn't mean that we are in a end of life or so. I mean, that's nothing. I mean, 2021 was energized on 2016. So it is just an outlier. But basically, in the beginning, there was a high failure rate because of the commissioning stages. This is the same thing, okay, but nothing is normal. As I told you, this is a very rare distribution. And you see here 2016, a higher failure rate in general. Okay, you see a more stable period here. Look, 2017 and 2021. Okay, this is the average for the 6 wind turbines, the whole fleet, pretty much. And then you realize that there are 2 clusters here. Okay, I didn't want to clean the data in 2022 because this was this anemometer failure. So I just took these 5 years, and you can perform a DUN test. Okay, it's a non-parametric test which work with the ranks. Or you can do some sort of clustering, but you already know the history of the wind farm. So I knew that selecting these 5 years, year 2017 and 2021, it was the right thing to do if I wanted a baseline for these machines. So average failure rate during these 5 years baseline per turbine at Kelmarsh, and here are the parameters. Okay, we can clearly see that, well, turbine 3 is what the more, the high reliable turbine when talking about hardware related failures. And turbine 5, it's interesting. Turbine 5, keep that in mind, which is the second best one. But you'll see what happened when I found when I did the simulation. Let's talk about yearly repay rates. Okay, you always in repair time you find this long tail distribution because you have either very fast repairing times, which is here, 20 repairs per hour. I mean, really fast repairing times, or you have a more critical failure where you have the turbine unavailable for maybe 2 days. So you have these extremes. You are always playing, with these extremes. Sometimes you have quick failures, like this converter not ready failure, and suddenly you have, wow, we need a spare part, and we need to wait 1 day to come with the spare. And you have these extreme situations, and that's why it is never normal. And in my experience, it's never exponential. I mean, failure distribution are exponential. That's a good model, a good PDF model. But the repairing times are not. So basically, I programmed a grid search, and I found what are the best fitting distribution for these repairing times and the parameters. Okay. So let's talk about here a quick stop in Monte Carlo, more than 1,000 years of service. Let's see what's about. Once I have the parameters, okay, of the distribution, failures and repairing rates, okay, I can start to sample or to generate random numbers representing the duration of these events. Okay, so basically here. What I'm looking for is what I want is the forced outage rate, which is the unavailability hours per year, okay, on the long run. So this is representative. So for instance, years since 2023, I started sampling per turbine, and until I found unstable behavior, and the probability multiplied by the hours of a year, and you have the different for or unavailabilities per turbine. Okay. The dynamic nature of the convergent process, you see here in Monte Carlo, which is basically, if, for instance, it's the same way if you want to find the probability of a fair coin, let's say we know it's a fair coin, you start just to make experiment, you throw the coin, and you then multiply, okay, how many heads divided by the total number of experiments. That's a Monte Carlo simulation. And here I'm just generating my experiment, the action of throwing the coin, is basically sampling or generating these durations based on the distributions that I found and the parameters. So it's very important to highlight the individuality of the process. No, that's per turbine, and look how different is turbine 5. I told you to remember that turbine 5 was the second best turbine with a really low failure rate. However, the repairing times were above the average of the other two. So basically, it matters. I mean, it's really it has a high weight, the repairing time, and you see that it has the 47 hours a year of unavailability or index. You see here the that what I found is really beautiful about this process is that, okay, you can't make this plot for a whole wind farm. Let's say you have a wind farm with 100 wind turbines. Okay, you can see here the distribution of the reliability index. Okay, you can see the distribution here, and you can see that you can calculate a median for the a baseline for the whole wind farm. So you know, okay, what's above and what's below. Okay, you have intervals there, and you can see here, for instance, you can see here that I just wrote 20 hours around here. Okay, 20 hours a year of unavailability per wind turbine. Okay, which means 120 hours a year losing at least 2.03 megawatts of available capacity for Kelmarch. Okay, that's the interpretation there. This risk of losing 120 hours a year at least. Why at least? But because there are situations that you could confront a failure of 2 wind turbines at the same time. Okay, and this risk only counting 819, which were the forced outages. Okay, in the scope of the presentation, but the total registered stop are 5,366 stop events. No, taking so these 20 hours per turbine, this risk is only is not counting scheduled maintenance, technical standby, grid, common mode outages. So it is really higher if we think about hours a year when you're not when you are not producing. Of course, all these stops are I mean you are supposed that you are generating at the time, because the turbine is working and it's stopped. So you are somehow losing this capacity, this energy sold. Well, let's talk about the system generation capacity curve, which is the real objective after you find these 4 indices with the Monte Carlo simulation. Okay. In operation, installed capacity becomes available capacity, and it is probabilistic. The available capacity, I mean, okay, you have the installed capacity, and you have an idea of the size of the field, of the number of turbines, but it's nothing, because you need a probability distribution in order to understand the available capacity of a power plant. And each power plant, each wind farm has its own distribution. Okay, it's like a signing, like very, very proper to the nature of that wind farm and the type of turbines and the size, number of turbines, very, very complex. I did this because I wanted, it was a very nice opportunity to explain the probabilistic nature of blackouts. You know that 3 weeks ago we had this blackout in Spain and Portugal. Okay, so I realized, wow, this is a good opportunity to explain the nature of these outages. Okay, so bulk power system outages like the recent blackout across Spain and Portugal are rare in robust networks. Okay, unfortunately, not in poor countries. In poor countries, blackouts are really, really normal because those networks are not robust at all. No? The challenge in identify a root cause, which they are studying. I mean, they are making reports and studying the case. Still, there is no final report. The challenge is in identifying a root cause lies in the fact that these failures often involve several independent grid, weather, and human-related events with overlapping durations. In other words, a chain of unlikely incidents all happening at just the wrong moment. So I did this exercise with Kelmarch to see what is bad luck, what is extreme to understand the nature of these blackouts. So a blackout is bad luck. Understanding the probabilistic nature of rare outages, like a blackout. To explore this, here's a simulation of an extreme case of independent simultaneous failure. The question, on average, how long should I wait to see 3 wind turbines fail independently within the same time window? Or more simply, how many years do I have to wait for the bad luck of having 3 turbines down at once just due to individual hardware-related failures? That was the curiosity and the analogy, okay, to understand these blackouts. So my simulation, this is the system generation capacity curve, okay? I had to generate a grid 2 minutes of 1,000 years in 2 minutes. I'm talking about millions of rows. Okay, this took a little bit. This took time. But once I got it, I observed the rare event 22 times in 1,000 years around. No, just to see how rare is that. So that means 2.2 times per century. So we can think on an average about 50 years. Every 50 years, I can expect to find 3 wind turbines down. Really, really bad luck. Okay, now, again, this is only forced outage. Think of maintenance when other turbines are down because scheduled maintenance or spare parts, really complex. Now, when you add in scheduled maintenance, weather-related effects, demand variation, forecast error, and 1,000 of the other interacting components, that average waiting time drops. No, so it's good to take into account the complexity of the system. Here is a zoom. This is a zoom of this first event. Look at this first. Look, all this black rectangle is 1 turbine down, which is very, very frequent. It's so frequent that it's a black rectangle. You have. I mean, in this zoom level. Okay, look at the year below. I mean, we're talking 2023 and 2000. I mean, year 3000. Okay. So, and this second rectangle here are 2 turbines. You see here the installed capacity 12.3 for Kelmarch. You have 1 turbine down. Your installed capacity is, well, minus 2.03. I mean, minus 1 turbine, and 2 turbines down, minus 2 turbines. This is the installed capacity, and this is the event where you have minus 3 wind turbines that I use as an example. So I'm going to zoom this to see. Not the nature, how did it happen? So look at this. Look at this. These are the 6 turbines, same colors along the presentation. And look at this. Here is the event. That first event, you have a very quick failure of the turbine number 1, but then you have a more maybe hours of failure for turbine number 2, and somehow turbine number 4 had was like maybe 2 days out. Well, not really. I mean, 2, yeah, maybe. So it overlapped. 3 turbines failed at the same time, and you have here the drop in the installed capacity. This is the system generation capacity curve. Okay, and you can calculate this distribution of your wind farm, and this is very important, the most important. If you have the load estimation for the next 50 year, okay, and how does the Kelmarch supplies the load? What's it's I don't know what's the configuration. If it's all you can eat, I mean, if it's always supplying when it's working, it depends on the operational constraints, of course. But if you overlap, if you have a probabilistic model of the load, okay, and you overlap here this system capacity curve with the load curve, you start to count every time the load curve is above the wind capacity, the wind farm capacity, you are losing energy. You are losing. You are not selling energy. So it's energy not supplied, ENS. And when you average this along the simulation, is the estimated energy not supplied, okay, which is basically money, okay, which is really the way to do this, not in order to plan and to for maintenance too, okay. So the big question and my vision, I mean, I have about 3 months before starting with Kelmarch, because I had an interesting case for a client. I have this question, okay, because I've done Fraunhofer, I've done a lot of machine learning and applied probabilistic modeling, of course, and the question is where and how risk engineering collides with predictive modeling, with machine learning. That's a question that I have in my mind. Integrating risk assessment can transform a typical time series forecast, okay, which is what you see today, very, very, very common, different, dozens of different methods, more into a more informative, probabilistic, and decision-relevant tool. So this is an example. Instead of just forecasting 16 gigawatt of peak demand tomorrow, which is what we find with any method today, with a risk-informed forecast, we might say there's a 12% chance demand exceeds available generation driven by low wind speeds and maintenance outages triggering a 30 minutes expected shortfall. I mean, this is a lot. In order to say that, you have to take into account the grid topology of the network, which is totally forgotten in a simple time series forecast. Okay, you lose the information of the grid of the network. It makes everything very, very more complex. But I think today we are in a moment that it's possible. It's possible to research and dig into this, in how to integrate and generate a framework to do this. Okay. So last thing, some takeaways. Like I told you, you can't always get what you want. This is some experience collected with this analysis. Okay, first, I don't see extract, transform, load, or whatever you call it, automation happening anytime soon in the area of risk assessment of power systems. Why? Because data transformation should follow a human-in-the-loop approach involving operators and maintenance teams. I mean, this is very, very different. This is really hard data to label. Very, very hard, because you need really expertise. What's going on with the turbine? Okay, it's really, really, really complex. Or with the grid and the topology. 20 years ago, I had to rely on universal parameters derived from IEEE standards. This is the Gold Book, 493, for equipment like high voltage circuit breakers. Okay, today the data are there, waiting to be organized according to those standards. Okay? Current data availability enables us to operate within a framework of probabilistic power system planning that goes far beyond traditional planning standards and practices. I think that we can do so much better planning with all this information in this way, in this probabilistic way, to working with distributions. Wind turbines on availability is underexplained. No, that's what we read at about 3% of unavailability. That's really, really underexplained. Okay, and likely underestimated. I took only 819 events from more than 5,000 stops labeled as stops. Okay. This is the number 5 is more on the programming side. Parallelized vectorized code makes it possible to run Monte Carlo simulations on modern laptops. Okay, when you have a lot of cores. Well, I have a powerful machine here at home, 32 cores. But I could plan a core per wind turbine. Okay, so basically you can get results in minutes. Okay, the Monte Carlo simulation was in seconds, really fast. But when you have to align the grid to derive the system capacity curve, that's really, really intensive. I mean, that's really, really, it's minutes. It's not more than 10 minutes. It's less, but it takes time. And we are talking about that, for instance, let's say that I wanted to see 6 components, the 6 turbines down of bad luck. Wow, I have to run million years, maybe. I don't know. But think about that. I mean, it's a lot of power. And okay, you could tell me, wow, you're crazy, but 6 turbines at the same time. But if you have a complex system where you have circuit breakers, you have power transformers, step-up transformers. Okay, if you want to model this, you need power here. Okay, but for simple analysis, you can do with a laptop today. That was really interesting. 20 years ago, it wasn't the same. I mean, it wasn't. I was not so optimistic. Number 6, there's a missing link. The question before, where exactly is the bridge between risk engineering and machine learning? This is a hint in one project that I had, but not related to energy. It was about predicting the failure of some elevators. I used I used reliability parameters as part of the feature engineering process. It was really, really interesting to use repair rates and failure rates as a column to predict as predictors, and I found really, really interesting results. I as part of the feature engineering process for a large XGBoost training algorithm classifier. Okay, not okay classifier. 7, this type of insight are gold for investors because I wish I had a failure rate at least or this 4 in index when I buy something. I mean, a wind turbine is clearly more expensive than a car. 8, I'm considering exploring this further in a more academic setting, maybe finding the right research environment and academic guidance, maybe. But yeah, again, 8 has to do a lot with the number 6, with the question, how can we bridge these two worlds? Because I entered what is today called data science. I come from this world, and it's a lot of data analytics and. Recently, well, like 5 years ago, they added chapters in the statistical learning books about survival analysis. But this was more related to the churning problem of subscribers or unsubscribers in Netflix, for instance. This type of problem that really triggered this type of analysis in survival. However, in power system, we are talking about repairable systems. No, there is no end of life. You're always replacing turbines, replacing components, transformers, and it's a little bit different. It's really, really different. So that means it. Yeah, that's all. That's the final slide. You can see here there is like an interactive report where I was playing with a package of tables ported from R, because now it's available on Python, great tables. And you can see all these numbers of all the indices, okay? This is a very simple model. This is a Markovian process to state, very, very simple. I would rely more on the Monte Carlo simulation because it gives you the real probabilistic nature of the downtime, the maintenance time. Okay, so yes, that's all. I think I'm done.
You're done.
Well,
fantastic.
Yeah, I'm done.
That's good. What's good?
Yeah, thank you. So
Yeah,
I've got my list of questions. So I'll maybe kick off with one and then open it up to the group. And my question is going to be around normal distributions, because in the wind industry, when we're looking at like pre-construction analysis, we're always using normal distributions.
Yes.
And in fact, with operational analysis as well, we've always got our P50, our P90 based on a normal distribution.
That's the classic evaluation. I know. Yeah. I mean, being curious, like, I mean, I was 22, 23 years old and I started this journey of stochastic processes. The dynamic theory of probability was very complex for me at that time. I have to tell you, I have to read a lot of Emmanuel Parsons stochastic process, really, really complex thing. But it was really interesting to dig into probabilities, starting with exponential distribution, where the mean and the median are not the same. So basically, my intro wasn't the Gaussian or normal distribution, was the exponential distribution to this world. So I'm used to it. I always calculate medians. I'm always, I'm always trying to look for what is outlier. What is it an outlier? Okay, so I don't know. That's a point. Yeah.
I mean, I wonder if we're missing out on a lot of the projects that, that are on the tail end of the spectrum, the ones that for some reason are like always beyond P99.
Exactly. Yeah. But I don't know. On the other hand, you have a lot of software like WinPro and all that stuff, but I don't know how's that working. I mean, the advantage of having data and you know what you're doing. Okay, you are censoring the right data. For instance, when you saw the yearly, failure rates, okay, I had to censor data because think of this: the machine is working in December, okay, and it continues working in January of the next year. Okay, that's normal. But I have to take out this time because it's divided in 2 years. I have to censor that data because the evaluation period ended. Okay. And I don't know if the machine never went down at the end of the year. So I have to censor data. And I was very, very specific about censoring this time to failure, these operating times. Or on the other hand, if the machine is stopped, is failed, the last day of the year, and it continues to be failed the first day of the next year, I have to censor that data point. I can include it into the evaluation. Okay, because it's a yearly failure rate, and this singularity is what offer trust to the investors. That's why I really think it's difficult for the moments, of course, for the months. I mean, things are really, really going fast right now, but to get trust from the investors, I think it's good to have all these open box. Okay, very, very clear of what are you doing with data, with this data, because it's really easy. It's really easy to get false numbers because it's very, very, very small numbers, failure rates. No, it's very, very detailed numbers, a lot of decimals.
Yeah. And I think what happens quite often with the secondhand wind farms is that availability might have been lower than expected, but it's always justified somehow. So you say, yes, there were these issues we had on site during this historical period, but they're not going to occur again because we've fixed things.
So, it's a renewal process, of course.
And to be honest, there's like the engineering side, it's backed up by evidence. You're like, okay, there's a root cause analysis, it's not going to happen again. But from a stochastic sense that yes, that failure might not happen again. Something else can.
Always. Yeah, it's very, very, very difficult. So, and when we talk about logistics and spares, availability of spares, wow, that's really, really difficult. For old wind turbines.
Yeah, as well. So, questions from the group?
Yes, Jorge. Okay, Jorge. Hello, Jorge. According to your experience, what would be the main drivers for purchasing to reuse power turbines? Okay, I mean, we can, from my point of view, suddenly, very soon, I guess, we will be negotiating reuse wind power turbines. So,
Yeah.
can you summarize for us what would be the main driver that I have to look at in order to be in the right way to?
Well, this is pretty. Yeah, this is a really good question and very interesting one, because you will never find open these failure rates from the manufacturer. I mean, that's really that's for them, and the way to find this is with operational data. Of course, the operators they do their own calculations, and sometimes they are in touch with the manufacturers because they have the field data. Okay, but I think the most important is to isolate the hardware related failure. Okay, this having reliable data labeled that these are the hardware related failures, not grid, okay, not other type, and to calculate these and to perform this type of analysis in a fleet of turbines, because it's not fair to do it for one. You want the distribution of the 4 index. That's what ideally what I have. If I have that, I can make a very really informed decision of what to buy. If you see the distribution of a fleet of Senvion turbines compared to the distribution of the 4 index for a Enercon wind turbine, wow, that of the same capacity, okay, same size and stuff. That's information that's gold. That's comparing two cars with different kilometers. Because remember something: when a turbine fails, it's more complex. When a turbine fails, okay, you have to intervene and to change components, okay, and you can damage the turbine doing so. Okay, because this is human error. This is typical. I mean, we were in utilities, and we know that there are a lot of human errors that you never know about, But human error is one of the first causes of failure in power systems. We know that. So basically, but it's usually not that reported. So basically, I would ask for the distribution of the 4 index, or I would calculate that if you are looking to have this contact with the operators, if you are working in the industry, if you have that, that's gold. Yeah, for the refurbished market. Yeah. So, more questions?
One that I like, Monte Carlo, again, is something that we don't actually see used very much in the wind industry. Why not?
I think because engineers tend to forget about money. Maybe we're too in, because if you think about economists, they are doing Monte Carlo all the time. Okay, and we are always more into the physics, because it's for passion. I can understand that, but when you start to you grow up professionally, and you start to consider money like we know. If you are in the industry, you know that's the main driver. That's true, and I think I don't know. It's not. If you think about it, I know that the Bayesian statistics do a lot of Markov chain Monte Carlo, to derive some intervals and stuff. But in the frequentist side of the problem, I don't know. I think if we start to think about EDC, estimated damage cost, cost of damage, damage cost, I think that's a way of think about this. And thinking about on the long run. What's the expected behavior on the long run to have this to compare, to establish a baseline, which is what I did with this system capacity curve. Imagine that I'm able to calculate the system capacity curve again the capacity of a wind of every generation plant is probabilistic, is a distribution. Imagine to compare that. I mean, that would be wow. For each utility should have this distribution of every power plant they owned but they don't. Okay, or maybe, yeah, there are one or two people interested. They have, but it's not that popular. It's not that well known for everybody. So I don't know. But yeah, I mean, I really enjoy doing this, and yeah, I think it's needed. I mean, there is a lag. I mean, there is a lot of work in the area, of course, of machine learning, of methods. Today, we see a lot of different methods to solve the same problem. You gain accuracy, like latest methods in machine learning, gradient boost methods, and yeah, I mean, working with PyTorch, and you always you want to reach a better accuracy, 1% more or 0.5% more. But doing so, you forget about that sometimes in a year, all your forecast is going to hell because it's going to be unavailable, the plant. And that's more important. There is a lot of more value saying that that turbine number five or 4 is going to be 40 hours, a year unavailable. Okay, that there's more value in that than providing a point forecast. And if I get together with the two, I mean, if I can combine these two worlds, wow, that would be amazing, which is the question that I have and the vision that I have right now.
Yeah, very cool. Okay, we've only got a couple of minutes left, and I want to hand the floor across to Florian. If you can just introduce the science project and data platforms briefly.
Yeah.